Folks, here's a couple of different standard types of impulse questions, or change in momentum questions. This one's about a roller coaster. We define some property of the roller coaster. It's moving up the hill, and it slows down, turns around, moves down the hill. What total impulse does the car experience? So, impulse, by definition, impulse, J, and or delta P, question mark. All right. I'm going to list some things we know. All right, here's what we know. Well, 1,250 kilograms. That's a mass. That looks like I wrote negative kilograms. I'll just write kilograms. How about that? Okay. Now, rolling up the hill at one speed, 8.5 meters per second. Rolling down the hill later at this speed. But, here's a really important thing. If we have up a hill, down a hill, those are opposite directions. I'm going to choose one of them to be negative and one of them to be positive. Up the hill, I'm going to define arbitrarily as positive. Therefore, our final velocity is negative. And okay, so now we want to know the total impulse the car experiences. And here are the things we know. Here is the thing we're looking for. So what equation has those things in it? Well, what we're sort of working with by now is a few different equalities. One is that there's this thing called impulse that by definition is delta P. And we've said, at one point what we said was that by definition, that force is the rate of change of impulse. Sorry, the rate of change of momentum. The rate of change of momentum. And therefore we can say that delta P is F delta T. And we also can say that if I know, well, this is enough to tell me an initial momentum. This is enough to tell me a final momentum. And I can certainly find a change in momentums by comparing final and initial momentum. So we can write this M delta V like that. All right. Mass times change in velocity gives me change in momentum. All right, and we know the M delta V part, or at least we know enough to fill that in. So I'm going to say here that delta P impulse is M times delta V. Well, that's M times V final minus V initial by definition. And that's 1,250 kilograms times V final, negative 4.5 meters per second minus 8.5 meters per second. So notice our change in velocity is not 4. Our change in velocity is negative 13, right? Negative 13. Yep. Okay, so this leads us to the fact that delta P is 16,250 kilogram meter per second. There's our answer. Meaning what? Well, the magnitude, how much does it change the momentum? The momentum changes by 16,250 kilogram meters per second. This part refers to that, well, there's a negative change, which means there was momentum up the hill. We ended up with momentum down the hill, so the overall change was down the hill. Or there's a change in the down the hill direction. All right, assuming that this takes 7.5 seconds, what average force is applied? Well, now we're trying to work something in here, so we can go a number of ways, but we could probably just say this. Delta P is F delta T. force, as we said, is delta P over delta T, or that's negative 16,250 kilogram meters per second divided by 7.5 seconds. And that yields roughly, kilogram meters per second, or kilogram meters per second squared. All those are newtons. Negative 2,170 newtons. Yes, I rounded a little bit. So that means 2,170 newtons down the hill. So what we got to imagine is why is this force down the hill? Well, what's making this roller coaster car slow down, stop, and speed up down the hill? Well, it's the fact that here's the car, and here's a gravitational force we could also write as m times g. And, well, quite honestly, watch this. If you take, where's my, there it is. If you take, here please, this thing, watch this, it's pretty neat. Groupity group. Do I need to? No, just take this. Watch. If I rotate this a little bit, and we sort of imagine like sort of tilting your head so that your head is like aligned with the ramp. Well, look, doesn't it almost look like, and it's actually true, doesn't it look like there's a component of this gravitational force that points that way down the hill? Yeah. Now, notice it's not the entire gravitational force that points down the hill, right? What's really happening is that group. What's really happening is that the hill looks like this, and FG points straight down. But notice this red part of the force here, right there, that part of the force is part of mg, part of the gravitational force that points down the hill. Down the hill, right? Down the hill. Fair enough? Okay. Now, let's see. What's the average rate of change of momentum of the car? Rate of change of... So let's just dissect this a little bit. Rate of... That means per unit time. Change of momentum. Oh, that means we want delta P over delta T. That's asking me for what the force is. I mean, it's not asking me for what the force is, but it's asking me for the same thing as what the force is, because the force is the rate of change of momentum. Okay, so what's the best answer here? I mean, the answer, it's fine to write 2,170 newtons. That's the answer. That's equivalent to the answer. It might make a little more sense in terms of what the question's asking to say, how fast does the momentum change? Well, it changes by 21 kilogram meters per second each second on average. But this kilogram meters per second is the same as kilogram meters per second squared is the same as a newton. So all of those are equivalent. No answer is more right than the other answer. Does one set of units maybe communicate the answer more clearly? Maybe. But neither is more right than the other. How do you know which units to use? You know, after a long time of doing these kinds of problems, you can say to yourself, well, you know, this is a nice way to talk about how quickly momentum changes. But again, it's the same thing as a newton, so it doesn't matter. Okay? All right. The big deal here is really keep your eyes peeled for this stuff about direction, up the hill, down the hill, and how you account for that mathematically, and having these lists of given information, right, like I've done here. And what I didn't do is explicitly say, okay, my initial velocity I'm calling positive because it's up the hill. My final velocity is negative because it's down the hill. You know, writing out a list of what you know, especially with the units and especially with variable equals, that can be a big help when it comes to problem solving. Okay? Okay, the next kind of typical impulse question is a graph question. All right? A graph specifically of F versus T, force as a function of time. All right, so we're going to consider, here's sort of our list of givens. Consider we have a mass M that starts at rest. Now, starts at rest means that the initial is 0. I bet we'll use that at some point. And I'm going to sort of arbitrarily say here's a force F, here's a force 2F, here's a time capital T, a time capital 2T, time 3 capital T. And we want to be able to identify some things in general here. So, number 1, what's the impulse during the interval time equals 0 to time equals capital T? What's the impulse? What's the impulse? Now, this is a graph of force versus time. So what we're going to certainly use is the idea that impulse and or delta P, same thing, is F delta T. All right, so during this interval from 0 to T, what's F delta T? What's F times delta T? Well, the delta T is clearly T. Time goes from 0 to T, so delta T is T, capital T. So how much force? Well, guess what? This is not the same, or whatever this object is, would not react the same way in the scenario you see on the graph as it would if there was a force 2F the whole time for time T. That's not the same thing, all right? This one says a constant big force is applied the whole time. This one says that a force that starts at nothing gradually increases until at that very last instant it's at value 2F, but it's, again, not a force 2F the entire time. So how do we handle this? Well, there's a simple answer, and the simple answer is you do this. You use the average value of the force. All right, and particularly because, excuse me, since the force changes at a nice constant rate, right? It starts at 0, the force starts at 0, and it changes uniformly, I call it uniformly, between time 0 and time t. The average value of the force, I mean, we can say that F average, or anything average, is initial plus final divided by 2, just like averaging test grades. All right, so this F average, delta P, F initial plus F final over 2 times delta T is, well, 0 plus 2F over 2 times capital T. So our delta P is F times T. Notice this average value of the function, the force function, happens to be right in the middle of the beginning force and the end force. And that's because this force changes nice and constantly, nice and uniformly. So there's our answer. We can only answer in terms of little f and big T because those are the only arbitrary values of force and time that we know. All right, the change in momentum from t to 3t. Well, we're going to do the same thing. J is delta P is F delta T. But once again, we have to use the average value of force over delta T. And our delta T here is defined to be 2 big T's, right? From T to 3T, that's 2 big T's. All right, so let's see. Our impulse, or our change in momentum, is, let's see, F average. Well, notice our F average, I'll do it again, F initial plus F final over 2 times delta T. F initial is 2F. F final is F over 2. And then our delta T is 2T. So that's 3F over 2 times 2T. Hey. Undo, I say. Right? Do. There you go. That is 3F over 2 times 2T. And that's just 3FT. I should have written these as little f's. Yeah, it's okay. There's our answer. Now, what's the final velocity of this object at time 3t? Remember back in the beginning, that velocity in the very beginning was 0. And we have a mass that we've defined in the beginning called capital M. All right? We want a final velocity. Well, final velocity also lives in our momentum, our change in momentum thing, where we say it's m delta v. Now, that's v final minus v initial. But remember, v initial we defined to be 0 in this example. So therefore, that can just go. And if we know the total impulse, we can find the total delta v. So what's our total impulse? Well, look, from 0 to t, we had that much change in momentum. From t to 3t, we had that much change in momentum. So our total delta p is 4ft. So that means that 4ft, there we go, 4ft equals m times v final, the thing we're looking for. So the only thing we can say is that, all right, v final is 4ft over big M. And we're done. Fair enough? Okay. So again, there are two main different types of impulse questions. One's more of a wordy problem, where they give you some numbers to deal with, and you have to be able to use some combination of all the stuff provided in this one big expression. Be careful about directions and up the hills and down the hills and lefts and rights and easts and wests and stuff like that. Remember, we said that writing yourself a little list of things you know can be very helpful when it comes to problem solving. All right, here we have to be careful with, like, this terminology. This says impulse, right? Well, impulse, you got to know what that means, right? Here we're rate of change of momentum being a little bit tricky about asking the same question we just asked. Sometimes that happens. All right, get familiar with your terminology. And then there's a force versus time graph. These are the other very common way to solve impulse problems, right? Where you're given force as a function of time. And just make sure that if force is not constant over any time interval, that when you want an impulse, use the average value of the force over that time interval. Okay? Okay. Very well.